episode of Undercooled, Materials Education Podcast. So once again, we have a special guest tonight. Spring has sprung, and we are celebrating Sunday with some materials education conversation. I have with me Peg Jones, who wears quite a variety of hats, but rather than me bragging about them, I will let her brag about them. So Peg, welcome to the show. First, thank you for coming. And can you just actually start with some self-introduction? What are some of the things that you do in the material sphere, and how did you end up here?
Well, I do best working in chronological order, so I'm going to turn back the clock to 1978. And I grew up in a materials household. My dad invented magnet materials and was a graduate student when I was in kindergarten at University of Michigan. So I grew up visiting Dad in East Engineering and got exposed to mercury in his lab one day. So that was fun.
You turned
Um,
out great.
yeah, but Dad smelled like burnt green sand. So that was my memory. But I intended to be a marine biologist from seventh grade on. That's exactly what I knew I would do. I would study phytoplankton and sail the world on the Calypso. And then I took my scuba diving final exam the weekend before I started college at U of M as an oceanography major and found out that I get really seasick with very small waves. So I
Ah,
needed a new plan, and I happened to be in the College of Engineering. That's where they stuck oceanography back then. So I took ME 150, or sorry, materials. What were we called back then? I don't even remember. M&M
probably materials and
150?
metallurgical engineering.
Yeah, I think so. MME. So, or MMSE. I don't remember. It's been too long. But
It
anyway, I
changed
got to
every few years
do,
back then.
yep, I got to do the class with Professor Flynn, and we had a lab. And I think the lab was probably what hooked me. But just to prove to Dad that I really didn't want to do this, because I told him all through high school how boring it would be to study gray lumps of things, I took the physical metallurgy class with Professor Hosford, the junior class, and ended up getting a degree in materials science and engineering in 1982. I worked in the foundry that we still had back then for Dr. Pelkey, and Dr. Flynn is an undergraduate research associate. So I think that probably helped shape my future. And I worked as a grader for whatever the 150 course was, the anonymous secret grader behind the scenes. And I remember writing encouraging notes on those papers, and here I am doing it again so many years later. I went to work at GE Aircraft Engine coming out of school, and when I was turning 30, I was trying to figure out if I was going to go finish a master's that I was trying to do part time while working 60 hours a week and traveling. I kept a packed suitcase for one of those jobs, implementing superalloys, um, or do the have kids thing. And I decided that the have kids thing was like an 18-year commitment, and I wasn't ready for that. So I went back for what I thought would be a 1 year educational leave to get a master's. And I had a husband and a mortgage, so I looked at what was within an hour of Cincinnati. And I ended up really being fortunate. I got an NSF scholarship to go to University of Dayton as part of a Women in Engineering program. And I ended up getting an accidental PhD by the time that was done. The market for jet engines crashed, and they kept saying take another year of classes. So I did. And then they said, you really have to take the PhD exams. And I said, I could never pass those. And they said, well, you'll be surprised. And that's how I ended up with a PhD. And then I started mentoring some graduate students at Worcester Polytechnic after I'd moved from GE to GM. And I was working for GM Powertrain on aluminum casting. And when I interviewed for that job, my only experience with aluminum castings had been way back working for Pelkey and Flynn, where we were melting aluminum and ramming molds and trying to do experimental work to verify some of the early porosity models,
Okay.
things that grew into things like magma. Um, but I was in charge of mulling the sand and ramming the sand and installing the transducers and the thermocouples. So when I interviewed at GM, they said, what do you know about cast aluminum? And I'd worked on superalloys and on titanium aluminides. So I said, it melts at far too low of a temperature to be useful in a jet engine. And they said, congratulations, you're hired. So I learned cast aluminum again. What I was really interested in coming to the automotive industry was being able to work on products where there's more innovation cycles in a career.
Mm.
I got a chance to work on the GE90 engine from scratch, literally from a blank sheet of paper to watching it fly over on Family Day. And you get about one per career in aerospace. So I really like the pace of automotive and the chance to make an impact on many different projects. But I brought my knowledge of fracture mechanics and fatigue to the problem of trying to design non-axisymmetric, very complicated shape castings in blocks and heads. And then, let's see, in 2009, I woke up and they said, congratulations, you're a transmission materials engineer and you have steel. And I said, okay, I knew that for a quiz in 1981. So I had to learn transmissions and steel. And transmissions in automotive engines were more dissimilar than jet engines and car engines. So one of the things that I realized coming from the jet engine world to the car engine world is if you normalize things by melting points or aging temperatures and yield stresses, we design in a lot of the same spaces. We have thermal stress-driven problems for takeoff and landings. You have thermal stress-driven problems in your cylinder heads as well. And then you have the rotating things and the vibrating things for high cycle fatigue. So that was great. And then I picked up, let's see, some of the electric motor applications coming from the transmission side. We were moving into the electric motors that are being released now. And then in 2018, BM decided to move my job to downtown Warren, which was more than 2 hours from my house, not counting traffic. And I said, well, you can move my job, I'm not coming. So I popped open Google, and I had always thought about being an adjunct professor at the end of my career, and it turned out there was a full-time tenure track position at Saginaw Valley State University, 15 minutes from my house, open. And it was specifically to teach the Intro to Materials course, which was something that I loved. So that's how I ended up here, just in time for COVID, and on the tenure track at the ripe old age of a lot. So it's been really fun discovering how to teach officially. I did a lot of teaching unofficially in industry because I mentored a lot of young engineers as well as the grad students. So that's the resume. You want to hear about the volunteer side, what I do with ASM?
Well, I guess that is officially the main focus for today, but that's such a fantastic story. And, you know, I've heard you tell it before off the record, but it's just such a great illustration, I think, for the audience out there that there's so many ways to go through life as a materials scientist or a materials engineer. There's really not just one track that we all follow. And the more stories that we hear about how many different ways there are to be in this field, I hope that some students catch wind of that and get excited about just all the opportunities that there are for them.
Yeah, and one of the things that I share with my students is even though I'm primarily a structural metallurgist, if you make castings, you have to know ceramics because of the cores and the molds. And when I came to GM to work on the aluminum castings, we were working on lost foam or evaporative pattern. So I had to learn some things about styrofoam. I worked on corrosion control for $1 million sets of tooling, so I had to learn some corrosion. And when I finished my PhD, I was working part-time at GE for my last 2 years. And I said, okay, I'm ready to go back to full-time. What great project do you have for me? And they said, flubber. I'm like, I just got a PhD in brittle intermetallic materials. Why are you making me work on flubber? But they were working on a silicone rubber problem, and they needed somebody to get involved with looking at the material properties of silicone rubber. So I got to learn some silicone rubber. So you never know where it's going to take you.
Absolutely. All right. Well, yeah, we did promise to talk about the teachers camps with ASM. I know you've been involved with those for a long time. How did you get started with the teachers camps, with volunteering with ASM, and what's your role in the teachers camps now?
Well, I've been an ASM member since I was a student, and Dr. Hosford put his glasses on top of his eyebrows and said, you will join ASM, it will be very good for you, and then they plopped down. And I was on the inner tube water polo team for the ASM chapter at Michigan, so I'm a longtime ASM member and volunteer. But around 2004, after I'd settled in at GM, I just had such a sense of gratitude for the teachers and the professors who gave me the gift of this career. Going back to Mr. Stuckey in high school chemistry, do it once, do it neat, do it right, was his slogan, and he taught us how to use the slide rule.
Perfect.
Yeah. Theoretically, I still know how. I don't think I do. And all those great professors at Michigan that I've mentioned. especially Flynn Hosford and the young Wayne Jones at the time, the new professor. So I felt so grateful, and I knew that the teachers camp was going on at Ann Arbor, so I took some vacation days to come help. And when you help at teachers camp as an engineer, it's very important to know that you don't teach teachers camp. You are there to make sure the coffee's ready for break and to answer questions. Um, we do cleanup in the lab if you need tables wiped down.
Mm-hmm.
So it's definitely a role of service and gratitude. So I got involved and started to take one vacation day, then it was 2 vacation days, and then it was 3 vacation days in Ann Arbor. And it was such a pleasure to be back on campus and to reconnect with, my U of M community too. So then I got involved in setting up lab tours, and I trained my boss that for 1 week in the summer I was going to be working from Ann Arbor, and if it was a desperate emergency, I would be at work, but he had to give me a head start because I was coming from a ways away. So I started um, moving into the Holiday Inn and staying with the teachers and coordinating plant trips, and it's been really fun. And I'm so lucky to have my co-organizers and to have the U of M staff involved as well. Um, Kathy Harrinan is kind of the grandmother of the Ann Arbor camp. She took it on in
Yes.
2002 when it started and is still involved. And she's a fabulous organizer and
Mm.
cook.
Yep, Dr. Kathy is one of the selling points of the Ann Arbor camp in many ways, all of the different aspects that she brings to it.
Yes. So that was how I got involved, was really just as a way to give back in gratitude for the people who had given me so much. But I also have done content development for the teachers camp. I did a series of experiments related to beam bending and lightweight design,
Mm-hmm.
and they were inspired in part by a friend's daughter who had bone cancer and was an amputee. And I get frustrated with the undergraduate textbooks because they're all about car parts and bulldozers and cranes, and my Barbies didn't have a Barbie Jeep. So when I was doing undergraduate homework, I would have to figure out what a tappet was, what it did, and then go figure out what I should make it out of and how I should make it, which was a
Mm-hmm.
lot of extra work. So I wanted to pick examples that could be relevant to a wide cross section of experience. So I thought, well, here's this amazing athlete, backpacker, who she cares about how much her prosthetic weighs. And we were able to interview her, and she's become a real advocate for prosthetic access. And her partner is actually a mechanical engineer who became a prostheticist and was able to give us inside access to the U of M prosthetics lab so we could
Ooh.
see the processes involved in designing and fabricating custom made prostheses. And we talked about the material choices involved in those prosthetics. So it's about a 100-page PDF with lab procedures that teachers can do at the high school level. I did hands-on chemistry with 6th graders in grad school, so that's part of what got me hooked on this. Um, let's see, what else have I done for the foundation? Well, I am a supporter. I've written a lot of checks to the foundation, and I'm on the board of trustees. So I bring kind of the voice of the boots on the ground to the board of trustees meetings.
Mm-hmm. I have to interrupt. I choose to interrupt with a brief backstory of Tim here because, I came to the MSE department at Michigan having never taken an MSE course, just being a physics student, right? And so I roll in and sort of say, I guess I have to start learning this stuff now. What are atoms exactly? I think chemistry was a while ago. And I was so fortunate that we were hosting the teachers camp that summer. And so 2 months after I started, I got to do the teachers camp for a week. And that was really, truly how I learned the fundamentals of material science and engineering, was just volunteering at that camp with the teachers for that week. And as you described, like, I'm in there just cleaning tables, right? Washing beakers, but you're immersed in that environment. And there's so much energy and enthusiasm. It's infectious around how cool this subject is, and the fact that we get to learn it and do it together, that really got me hooked on the community, right? The materials community, as well as uh, actually starting to learn a thing or two about, I don't know, phase diagrams or some crazy stuff like that. But
Yep.
yeah, great
And
experience.
yep. And I mentioned that we don't teach the teachers can't, but I forgot to say who does. So we have a talented group of about 35 or so high school, we call them master teachers. They teach material science at the high school level, many of them do. Some of them teach it in career and tech programs. They have 2 years of material science at the high school level in some of the tech programs. They're amazing. We also have teachers who are teaching the baccalaureate chemistry or AP chemistry, AP physics, and then some general engineering courses. So they find ways to slide it into all the other courses, but we are so lucky to have them because they teach not only the content of an introductory materials course, your metals, ceramics, polymers, composites in a week, and it is a fire hose, but they're also teaching the pedagogy, the how do you teach this, and how do you teach this on the cheap.
Right.
So we don't use glassware if you don't need glassware. One of the teachers that was involved in this from Ohio talked about starting their career tech program with no money, and they had students bring in used salsa jars. Used salsa jars make excellent beakers, and they're free. So we're using dollar store plastic cups and craft sticks. So it makes it so accessible, and teachers can go home and implement the activities that they learn. The other thing that makes it great is we're out of the classroom probably somewhere between a third and 2/3 of the time during camp. So it's very much hands-on and experiential learning.
Hmm. You know, as you're talking about salsa jars, one of the lessons that I've learned that I brought forward from the camps into my own teaching, and so I'm hoping we can talk about what are things that we do at the university level with our students that we've adapted or upscaled from the teachers camps, is the value of low budget experiments. You can spend very little money on something and have it be a very rich educational experience. So as one example, in my functional materials lab class, we do batteries for a month, and the students are building ice cube tray batteries, right? They've got 12 cells in an ice cube tray, but after the initial sort of like, I did this in high school, okay, well, once you convince me that you can apply the electrochemical series correctly, that you can explain why your voltage is half of what you think it should be according to Callister, once you can tell me, where did my electrode go? I thought I used to have one here, right? There's a lot of richness to these experiments that we need to try to really understand and explain all of it. A couple dollars worth of wires and salt water can be a month's worth of discussion in a junior level lab. There's so much that we can do to bring some of these like middle school and high school level experiments to the college level. So what are some that you have brought to your classes?
Well, thanks for the segue. I'm teaching primarily first and second year undergraduate students in a teaching institution without graduate students. And I'm in the mechanical engineering program. So there's a lot of things I don't have. But one of my favorite assignments was one that I put together during COVID. I need to find it. Sorry, I thought I had it handy. Yeah, here we go. So this is my very first, oh, it would help if I shared my screen, right? Oh, Tim, hang on a second. There we go. So one of my very first activities that I do in ME250, which is the Callister course.
Mm-hmm.
I'm being klutzy about this because I'm trying to talk and do something I've never done before at the same time. Here we go. Scaffold's lab report writing, because I have to teach them how to write formal lab reports.
Yes.
Yeah, and most of them went into engineering because they think they'll never have to write. So
which is the opposite of the truth, of course.
Yeah, I stole this from Teachers Camp. We do an activity with Portland cement, making composites, and we drop test little pucks or discs and figure out the fracture energies. And we do that very qualitatively in camp. You can also do that with ice. And this is based on, I think it was called Pycrete. Back in World War II, somebody wanted to create an unsinkable aircraft carrier with sawdust and ice.
Oh, yeah, I've heard about that.
Mm-hmm. So, and you can look on the hydraulic press channel on YouTube and find them testing Pycrete. But this was an example of a student that lives in the dorm, and she didn't have access to much, but they have to make the same size composite with just plain ice, and then with ice and shredded paper. Ice and toilet paper is fabulous. She happened to choose oatmeal, so they had dried oatmeal around.
Okay.
So she's documenting her procedure. See how she's got figures?
Mm-hmm.
They haven't done this before. And she drop tested these. I've actually had to put a safety requirement on this assignment because I've had students climbing on garage roofs to drop things.
Well,
So
their
she's
commitment to
documenting
science
with
is
a
commendable.
scale. Mm-hmm. Yeah, so here she's using to take documentation pictures with
Oh,
scales.
I love the scale bar. Yes.
Mm-hmm. And she lived in a dorm with an exterior stairway, so she was able to drop
Oh,
from pretty
perfect.
high heights. But they've had physics.
Mm-hmm.
When was the last time they calculated potential energy? Okay. So they had to describe what constituted the first crack, what height corresponded to the first crack, and what height constituted significant damage. And this one isn't as good because of the shape of the ice cube. A thinner puck is better. But she didn't have anything to make that shape. So you can see she's thoroughly documented. Okay, but here she's calculating her mass of her cubes. And here she's converting feet to meters.
Good.
She's coming up with the energy. So they've had to learn how to use an equation editor and put the equation number, and the equation number needs to be mentioned in the text, all those things that we know to do. She's connecting the variables with the units, which is always a struggle. And she's had to fill in a data table. So I don't tell them what significant damage is. They have to decide that. And the reason that I don't tell them is because if you're the design engineer responsible for a component, when that component finishes a dynamometer test, you're called down to decide if it passed or not. Nobody decides that for you. Now you can see she's got the table 2 here labeled on the wrong side. That's okay. We'll fix that. So I didn't create this originally as a writing scaffolding, but it works really well for that, for the basics of lab report writing. The other thing that I like about this, and I'm going to stop sharing, is it allows me, hopefully that's back to normal for you, Tim.
Yes, looking good.
Okay, it allows me to introduce that tetrahedron concept of we are varying chemistry, processing, to create a structure that has certain functional properties. So in the very first week of class, they are discovering that, hands-on, and I don't need any special lab equipment for them to do it. I use water because they don't need a kitchen scale, they don't need a lab balance. We know that certain milliliters of water weigh a gram per milliliter. So, and it's close enough. You know, if you have about the same amount of water in both and you're using oatmeal or shredded paper, something very light, ignoring the mass of your reinforcement really isn't a big deal.
Mm-hmm.
So it's been a good semester starter, and it lets them know, hey, this class is going to be weird right from the get-go.
Oh,
So that's one
great.
thing that I do.
I love the hands-on component to the homework also. It's not just, okay, now go to problem 7 in chapter 4 and solve it.
Yeah,
'Cause
let's
you
find
can,
X yet
but-
again.
Right. That's also not real engineering practice any more than ignoring writing is real engineering practice.
Right, and they come back the second week of class, and now they have something to talk about. So I'm building that community of learners as well. Another thing I pulled up that I wanted to show you is my grain size assignment.
Yeah.
Okay, so this is one that I also came up with during COVID. Another hands-on homework. So we learned the linear intercept method of finding grain size from Callister. See if I can make this big. So I asked them to find a galvanized object somewhere on campus. We have bike racks, we have light poles by the Student Recreation Center. I have a couple of objects stashed in the lab to help them out. So they have to take a picture of their object with something in it for scale because they don't understand what magnification is. And then they have to do, and I like the box with the X in it for counting our intercept. They have to count the intercept, and calculate the grain size using the same formula that we use in Callister with easily seen pictures in Callister. And then I ask them to choose 5 random grains and measure those and do a common sense check of the number that they calculated. So that one's been fun, and that's something that you could do without access to a lab per se. They all have their cell phone cameras, and I can put out a few rulers. A lot of them end up using their student ID. Oh, sorry, I'm showing you something. I'm not sharing my screen. A lot of them end up using their student ID as a reference dimension. So Tim, let me go back and I'll show you what that looks like.
So what are they measuring the grain sizes of, or how are they coming up with specimens to investigate here?
So if they go by our student rec center, there are light poles that have gigantic, like foot-size grains. If they find bike racks on campus, they're smaller. They'll have HVAC ducts in their apartments or in their homes. But this is one of the objects that I got from Goodwill that I stashed in the lab.
Oh,
so
great.
It's some kind of a little decorative thing. Yeah. Sorry, this is what I was showing and explaining without showing it. So they have to take a picture with scale. They have to figure out the magnification. Here's their point count. And then I'm asking them to evaluate their calculation result by comparing it to 5 randomly selected grains. And they learn that it's hard for humans to make random selections.
Yes, it is.
Mm-hmm. Yeah, so this week we're going to be learning about time temperature transformation in my class. So that's Callister chapter 10. And one thing that I started to do is I've got my shape memory wire that we all love to play with in camp. I have them wrap a circle of it around their finger, and they hold one end of it with pliers, and I have blow dryers in the lab. And a lot of my male students have never used a blow dryer before, so that's a big mystery to them. But I have them time how long it takes for the wire to start to move, how long it takes for my circle to be half open, and how long it takes for the wire to be back to straight, with the blow dryer on low and on high settings. And we plot those data points on the whiteboard. We use a hand-drawn log scale. It's real quantitative for the time. And so they have 0% transformed, 50% transformed, 100% transformed at 2 different temperatures. Right below that, now we have a TTT diagram with the y-axis being temperature as opposed to percent transformed, and the x-axis is time transferred down from that upper curve. So now they get to sketch out the very beginnings of the idea of a TTT diagram, and they've done it for free. I can reuse my shape memory wire. The blow dryers are sitting there. How much does a blow dryer cost? So yeah, it's been an effective way to help them understand what's really going on with the TTT curves.
That's phenomenal. There's so many good things. So many accessible, truly hands-on, tangible experiences like that just make more sense to the students. It's not the same when you have a magic black box that is extremely expensive and fancy and will report all the numbers with all the significant figures, but it's just a computer spitting out numbers, right? When you hold it and when you do it, there's a lot more reality to that experience that helps you make sense of how physical objects in the world really behave.
Yep. And they get to work with a partner who gets to use their cell phone for a timer.
Ooh.
And we talk about, is that any more accurate than my 1 Mississippi, 2 Mississippi timing?
That's a question I love to ask in classes, is when we have multiple options for how to measure something simple. And it's like, I don't want to use a ruler. Why not? Rulers are great tools. Can you do better than a ruler? Maybe. Let's find out. There's only one way to know, which is not to assume that one device is better, but to measure and look at the statistics and say which is more reliable, which is more accurate, so on, so on.
Yep. Yeah. So another thing that I stole directly from camp that'll come up in a couple weeks when we get into heat treating steel, which is Callister chapter 11, is the bobby pins and paper clips.
I
love
pins.
doing it.
I'm doing them Tuesday with my freshmen, and I'm so ready for it.
Yep. So I actually invest, and this is out of my pocket, in the big bobby pins made for holding rollers in your hair, because I think you can get a better sense of the change in the strength. So if you're not familiar with bobby pins and paper clips, you need a propane torch or a Bunsen burner. So we heat just the loop part of the bobby pin in the propane torch, austenize it, quench it. You have about 1 second for 1080 spring steel to get that in the water. Hold another one in the flame, slowly withdraw it from the flame so you're normalizing. And then we'll do a second water quenched one. So we do the same treatments to paper clips, which are mild steel, down close to 1020 to 1030 range. And they will respond differently because the chemistry is different.
Right.
So I ask my students to test the springiness of the bobby pin, and they have a control. So they opened it about a quarter of an inch or so and let it snap back on their fingers, which hurts. So they remember.
Yep.
Um,
Yep.
and then, of course, our brittle martensite, untempered martensite, will snap. And the looks on their faces when they realize they have just broken a piece of steel is worth doing it, just for that. Then they'll take their air cooled one and they'll pry it apart and see if they can make it straight. And they find out that that little loop part that was
Mm-hmm.
heat treated is actually pretty hard to push down with your finger and get it flat. Then I ask them to put it back together. And you can actually do stress relaxation. If you take that ductile bobby pin that you've shoved back together and you hold it in pliers over a candle flame, you'll
Mm.
feel it trying to pry the pliers open for some amount of time. And then eventually you stress relieve it and that stops. So
Oh,
that's
that's
an
great. I haven't
interesting
done that
extension.
addition.
My students came up with that. I didn't. And then we take our last water quench bobby pin and we do this as a class. They each pick a different tempering time and we temper in a candle flame. And
Mm-hmm.
our y-axis for that is just, is it brittle, is it springy, and is it ductile? And they're amazed that they can get springy back.
Yeah.
So it takes all these vocabulary words and concepts from heat treatment of steel and they get to do it. And when you do the paper clips and it doesn't do the same thing, it's such a great way to reinforce that idea of I changed the chemistry, I kept the process, something different happened. So we're going right back to week 1, now that we're in about week 13.
Mm-hmm. When I first started blacksmithing just for fun, and started working with just good old wrought iron, like, 0.1% carbon or something, it took me a while to overcome that bias of like, there are things I can't do with the steel, right? It'll become brittle. There will be too much martensite. And eventually I get my head into like, no, it's just iron. I can do whatever I want and it'll be totally fine.
Mm-hmm.
But yeah, it's just that same thing. It's the bobby pins versus the paper clips. And yeah, 0.5% of an ingredient can kind of make a world of difference, which is also something that's hard to appreciate when you're a beginner at this, to know that a couple tenths of a percent is actually a really big deal sometimes. I do have one more question about the camps, which is what's new, what's up and coming. Are we developing any new content, new ideas and
Mm-hmm.
activities to keep growing these forward?
Mm-hmm. We are. So I was just at ASM headquarters actually last weekend. And we were working on 2 things that I think will be added to the advanced camp. So we have a basic level camp and then we have an advanced camp for people who are really going to teach a material science elective in high school, can probably invest in a furnace and do more of the hot work. But last year we tried to add some biopolymer content to get at some of the sustainability themes in materials.
Ah, okay.
And people had trouble with it. Things didn't always polymerize or cross-link as you expect. A lot of that is starch-based, and if you're in camp in Houston and it's humid and there's a high mold count, your biopolymer is subject to mold. So we wanted to troubleshoot those a little bit. We picked one good one that I think can be extended. It uses basically edible ingredients, and you can do a scientific method exploring the effect of the amount of plasticizer or the type of starch, the processing time, and it's just done in a cup in a microwave. So that one has some good potential. We need something that can happen fast, because if you try to do things like make a film with the biopolymer and it needs to dry for several days, if you're in a camp in a humid area, that can be an execution problem in 5 days
Mm.
of camp. And, teachers have to move on too during the school year. So we need things that are going to be time efficient. The other thing that we're doing that is so wrong, is just so wrong, and it's going to be fabulous. Um, One of the teachers in Ohio found this. She's very interested in glass, and she likes to do uh, glass slumping, and then there's a kind of glass art form where you put pieces of glass onto a substrate and they fuse.
Okay.
So this is a variation on that. So she took glass powder and you mix it with a little bit of just drinking water. We had bottled water, maybe a tiny drop of jet dry. So you mix that together, and it has to be pretty runny. That's one of the tricks to it. And then you put it in a candy mold, just a silicone rubber candy mold, and you freeze it after you've packed it down really well. And as you pack it down, some of the water is going to exude to the top. So you want to
Mm-hmm.
wick that off with just a paper towel, freeze it, and then you pop it out of the candy mold and you put it right in your kiln, right on kiln paper. And then we fired them overnight. And the glass particles fuse and you get a solid glass object. It's sintering. It's what we do with powder metal every day. And we say, okay, powder metal, we got particles that touch and atoms jump across and they build the bridge and we get sintering. You go, yeah, I put metal in a furnace, I got hot stuff happen. There's something so wrong about putting an ice cube in a
Uh-huh.
kiln.
And turning it into glass.
Yeah, and it comes out, it's a miniature version of what you molded, and it's retaining quite a bit of detail. So I think
That's
that one's
really
going to be a winner.
interesting.
Mm-hmm.
I'd love, and things that upscale as well. I could totally do that with my students and then say, okay, now let's throw it in the SEM, right? Let's look at what's actually happening at the interfaces of these particles. You can take it as far as you want.
Right, right. And if you let the ice cube melt and you touch it before you fire it, you're done. It's just
You're
a pile
done.
of dust. So
Wild.
I was thinking originally that there might be something going on with like hydroxyl bonds from the water, but it doesn't seem to be that. I think it's just mechanical interlocking from the packing, and then as long as you don't disturb that, you'll get the sintering reaction.
Hmm.
So that was fun.
Awesome.
So we haven't touched on my magic numbers yet. You want some
Oh
numbers
yeah. Yeah, let's brag about how
before we
awesome the
wrap up?
camps are. Because, I the brief intro here is recruiting is the perennial pain point for MSE, right? Nobody knows who we are, nobody knows how great we are. We know how great we are, but reaching not just freshmen, but in this case reaching high schoolers, right? To get students before they come to college to say, "Oh, I could do that. I could see myself going there." Unfortunately, not everyone's dad is a material science student, so
Mm-hmm.
we have to find other ways to reach people. How many people are we reaching with the camps?
Yeah. So I looked at some TMS data from the 90s, and 40% of us knew somebody in the field.
Wow.
Yeah. So the teachers camp started in 2002, and they've kept track of how many teachers have participated since then. So as of last summer, we were up to 13,491 teachers. So they estimate that each of those teachers will touch about 1,000 students in their career. I think that's really an underestimate. So that means we've exposed 13 million K-12 students to the idea that materials is a career.
That's so amazing.
And this summer we've got 36 basic curriculum camps planned. 8 of them are residential, which means you get to stay on campus or in a nearby hotel, and it is free for the teachers. There's going to be 2 advanced camps. They're residential. There's a virtual camp on sustainability. There are 2 materials genome camps, 2 K-5 camps. We're getting into elementary.
Wow.
The elementary teachers love it. And then there's going to be 3 year 1 virtual camps or basic curriculum virtual camps, which we started during COVID. I was involved in trying to figure out how in the world are we going to do this during COVID.
Mm-hmm.
And it makes it possible for people who can't physically attend a camp to still benefit from the program. And it's very cost effective. On the student side, if a student hears about materials from their material science high school teacher, how do we pull them in? So I looked this up for our conversation, I knew about the Eisenman camp. The Eisenman camp is fabulous. It's at ASM headquarters. It's 1 week a year.
Right.
So it's based on doing a lot of failure analysis, typically. So there's 32 high school juniors going into their senior year and about 12 professional mentors working with them. They have the run of the lab at ASM, and they do field trips, and it's a great program. Um, However, in addition to that, there are 15 camps that are planned for high school students in the US, India, and France. France used to have one, they're up to multiple locations this year. So, looking at the stats since 2000, so we actually started the student camp before the teachers camp, 19,065 students have come through.
Wow.
Of those, about 49% who participated in the Eisenman camp have gone on to major in material science.
That's incredible. I think that's the number I at least really wanted to hear is how effective are these programs, right? If you're getting half of participants, that's an incredible
I know
rate of
it's half of
success.
32, but that's still a lot.
Yeah,
And
absolutely.
and the fact that there's these other student camps to help leverage what students are hearing from their teachers and then get to go do something hands-on. They're not all week-long camps. Some of them are half a
Sure.
day, some of them are a day. Yeah. And I
Wow.
think one of the other big news items was Apple hosted their first teachers camp last summer.
Ooh.
And they weren't sure, and they kept it all hush hush. And by the end of the first day, they were talking about, we're having you back.
That's great.
Yeah, and their employees were involved in volunteer positions as well. One of the concepts that came from that I heard about at Master Teacher Training was the rock to metal ratio. So one way that Apple is working on sustainability is for each of the metals that they use in their products, they're figuring out
Hmm.
how many pounds or kilograms of ore and waste products are required to generate a kilogram of that metal.
Yeah.
So they worked with one of the government agencies. I want to say NGIS, but I'm not sure that's true. Anyway, one of the geological agencies was involved in helping them get the physical science data to do
Hmm.
those kinds of calculations. So I think when we look ahead in our sustainability camp, we'll probably be starting to talk about rock to metal ratios, even in our basic program, because it's
Mm.
such an easy way to relate to it. And I mentioned to you that they ran your malachite lab last week.
Yep.
That was in conjunction with the rock to metal ratio idea. So, for those of you who don't know, I'll report on you for a second.
Sure.
Tim has a great way to do a copper ore reduction lab. So he takes a piece of lump charcoal, drilled a blind hole in it about a half-inch diameter, Tim,
Yep.
maybe about half-inch deep, maybe a
Yeah,
little more.
that's about right.
So we put just a chunk of malachite copper ore down in the hole, and then you heat that with, you've got a MAP gas torch or does propane work?
It's just propane. It's just a big angry propane torch.
Okay, propane torch on top of the lab table. We're not in a fume hood. I think they took it outside at ASM headquarters in the snow. But if you heat it long enough, the malachite will reduce and you'll get a little droplet of malleable copper out. So they can start to look at the weight of the particle that they processed and the mass of the copper that results.
Hmm. Yeah, doing that quantitatively is something that I haven't done with students yet, but now that you've got me thinking on the sustainability angle, right? That's the perfect question to be asking is what's the yield for this? Is it actually an efficient process? Could it be made better? I think there's a lot of questions of optimization here that students maybe overlook because they're like, people have been doing this for thousands of years. It's all figured out. No, that's not actually true. We have figured out ways to do this. Let's not assume that we know the best way to do it just because a way has been found.
Mm-hmm. Good. So that's everything that I had written down on my list of notes for our conversation. Did you have anything else?
Well, something you alluded to earlier, setting aside the teachers' camps a little bit, but another conversation that I've been having with a lot of people is just the fundamental skills teaching that we have to do, which you brought up, like how to write a lab report. Actually, really important. Also, something students apparently don't learn. But the thorn in my side lately is math, of course. And that can be how to solve partial differential equations, but it can also be how do you make and use a histogram? That's just important and just as vexing sometimes. So I'm curious to hear if you have any things that you've been doing or tips and tricks for getting students into more of this like numeracy, data literacy kind of space of just working with data intelligently.
Yeah. So I think this may be an area where having the industrial experience I bring is helpful because I can give them real life examples of how do you use common sense? How do you learn to think like an engineer? Um, I'm teaching the Intro to Engineering Data Analysis class, ME202. They may not have calculus yet. They're allowed to take it concurrently. So the idea of thinking algorithmically through a multi-step problem is still very new to them. They might have plugged in x and solved for y, like y is x squared, but tackling engineering problems is not something that they know how to do. And we think we're seeing COVID algebra impacts. I had a student say to me last week, I understand calculus, but I can't do the algebra because of COVID and it messes up my calculus. But I understand the concepts of calculus. They just can't get the mechanics of the algebra. So I see it a lot. I write my problems on quizzes and exams. What are the steps and the formulas needed to solve this? I want them to get the idea that having a plan is a good place to start.
Yes, absolutely.
And I make them draw sketches. So we just covered diffusion in 250. And if you're sketching a diffusion problem, I want you to label the surface composition, the target at some depth, and the starting composition of the material. I want you to draw the concentration gradient. Are you working a fixed first law or a fixed second law problem? If you're not clear on that, where are you going to go? Okay. So I'm asking them to extract things from story problems, and they're not good readers, and identify a problem-solving strategy. I will give them a table to fill in for their answers, and it has the number and it has the units as a separate column in the table to try to get that muscle memory that when you write a number as an engineer, there is a unit.
Mm-hmm.
And I'll take points off for no units.
Oh, absolutely. I was grading homework for my freshman last week, and people are writing things like watts per hour, which physically possible? Sure. I could imagine some quantity in some equation that's watts per hour. Is that what you meant? No, absolutely not. You meant kilowatt hours, right? And yeah, these distinctions are things that I am finding we really have to explicitly teach at the college level.
Yeah. And I'm grateful that I knew how to use slide rules, because with a slide rule, you manage your exponents separately.
Right.
And they have no concept of exponent management. And if they miss a minus sign, like an e to the minus something in the diffusion equations, where you should get a tiny number and they get a huge number, they don't know where that came from, that it's the missing minus sign. And I drive them nuts. I'll write formulas out on the board, and I'll pull my exponents off to the side. And one of my students, who's currently a senior, said, "Why do you do that? It bothers us." Well, I do that because I'm managing exponents, and I need to know if my final answer makes sense.
Right.
And if I just type everything into my giant number-making machine, and I've got a parentheses problem, I'm not even aware that it exists. So I'm dealing with my friendly little numbers over here, and I'm putting my exponents off to the side. So they don't like it, but I'm old school.
Oh, I think there's value in that. As you're talking about the thinking like an engineer and this very related engineering judgment kind of concept, one thing that I feel is very important is being able to know ahead of time what order of magnitude should the answer be, just in a physically reasonable sense, right? Are we even talking like KPA or MPA or GPA? Let's start with that. And if you're ending up with a vastly different prefix in your answer, maybe the math is the issue.
Yep. So what else do I do in the way of teaching that? I'll essentially race them on the whiteboard. I'll be estimating what my answer is, and I write out my steps. Like, here I'm multiplying this, and this is about 3, and this is about 2, and then I've got this about exponent. Okay, what did you guys get? And they're usually really surprised at how close I am. And I tell them doing algebra in public is kind of scary for me because I'm a little math phobic.
Right. That's also something that's so important to communicate to students is these are the things that I'm still not comfortable with because we all have them.
Mm-hmm.
And I think, unfortunately, there are a lot of faculty who pretend, at least in front of the students, that they're not afraid of any of this or uncomfortable with any of it. And if we can
Yeah.
show
I
the
tell them the
students,
first time I met the error function.
it's okay to not be totally confident in what you're doing, but to still say, I'm going to work through this and get to some kind of resolution despite my own hesitancies.
Mm-hmm.
That's how most of us feel when we're working through problems, that we don't know what the answer is. If anyone knows the answer, and they need to see that and understand that it's normal.
Mm-hmm. Yeah, I tell them the first time I met the error function, my brain kind of went earth.
Yeah.
It was overwhelming. But I talked to them about when you look at the error function tables in at least my text, they're set up backwards. They're set up with z, the value inside the error function argument, and the error function. And we read left to right. You have to read the error function table right to left. So we work on that. We work a lot on linear interpolation. They get confused about how to do that.
I still have juniors doing the classic, I need the slope of a line, I'm going to grab 2 points. And they always grab 2 adjacent points on the line.
Oh, it drives
And
me
it's
nuts.
like,
Mine do
if your data have
one.
any noise whatsoever, and then they're asking me like, why did I get 30 GPA for the modulus of my aluminum? And I'm like, how did you calculate the slope?
Somebody taught my students to take 1 point and get a slope. You assume it goes through 0, 0.
Do you now?
Oh, yes, you do,
I
but not
see.
explicitly. So, yeah. I see
Okay.
a lot of those errors.
Well, eternal vigilance.
Mm-hmm. Yeah, the one last thing that I had in terms of teaching numerical literacy is, well, besides try to do it hands-on where you can, I talk about how engineer numbers are better than the math department numbers because our numbers come with a premium units upgrade. And I keep reminding them of that over and over and over again. We're better
Right.
because we have units. We're engineers. Yeah.
Hey, whatever it takes to get the kids to eat their vegetables, right?
Mm-hmm. Oh, we eat Rice Krispie treats. When we're learning about
Because
fracture
they're
modes,
composites, or
we test the fracture behavior of a polymeric composite.
very clever.
They stretch them. They can watch the ductility of the marshmallow tendrils. We can observe whether it's intercrispular or transcrispular fracture. They can put them in the freezer. They can try bending, torsion, and axial tension.
Right.
And then in the end, I asked them the first time I gave the assignment, so did any of you do a compression test? I said, no, that wasn't in the instructions. Did you eat them? Oh,
Right.
how did it fracture? How is it different? Yeah.
Mm-hmm.
But they're tackling intergranular, transgranular fracture modes. So those are new terms to them, and they don't exactly roll off the tongue. But when we
Right.
can joke about this was transcrispular, then they remember it better.
Of course.
And I get to pass them out at the end of the quiz. Yeah.
Yep. Great stories all around. We've been talking for almost an hour, so we should
Sorry.
probably wrap it up. No, this was a great conversation. I'm really glad you came and we got to do this. And I guess I'll see you this summer, if not sooner, at, of course, the Ann Arbor Teachers Camp. But before we sign off for today, I want to ask the standard question. Is there anything else you want to brag about for the audience? Anything you want to advertise? Anything you just think people should know, as long as you're, going to be famous on the internet? Here's your platform.
No, just thanks to everybody who's helped me along the way. And I'm so excited to be at this stage of my career in creating new engineers and thinking about what they will see in innovation and in what they'll be able to create through what hopefully they're learning from me to some degree.
Yeah. Well, with that, I think it's time to call it a day. To Peg, thanks just one more time for coming, spending this time with us, and to the audience, As always, we'll see you next time on the next episode of Undercool.